Okay, so today we are going to study cameras and image collections. And basically, we are going to use cameras to collect data from the 3D world, and then so that you can do analysis and generate 3D content from AI graphics. And also, image collections are the product of cameras, but generalized camera systems, what they call like a computational photography. And this would be a way to create the data sets that we need to do training for various purposes in AI graphics. Okay, so the outline of the lecture is going to be, first, we are going to discuss the mathematical concepts, and we are going to discuss a very important thing, is that the plein-optic function and the light field. So that is actually the information that's captured by the cameras. And we are going to convert this into good mathematical models, right? And then we are going to focus on image acquisition. So basically, how to capture the plein-optic function through light fields. And we are going to analyze this sensing devices. So there are cameras, different types of cameras. And one important element is the optics, or the lenses that are used to gather light and then that go to the sensor. And then we basically are going to collect light rays. And then we are going to model these light rays in different ways. So with that, we can have systems that are from computational photography, the smart acquisition devices for visual information. And so these systems are going to produce image collections. And actually, the image that you see on the internet that you can also use for training, they are produced by cameras in different fashions. And then this leads to computational photography and vision. And we are going to kind of give a framework of how to understand the collection of images, so it makes sense that it will be a data set for training. Okay. So we're going to start with this. This is the plein-optic function, and it's the most important mathematical concept related to vision and graphics, because the plein-optic function is a mathematical abstraction that basically is a complete description of visual information in a 3D environment, right? So you can imagine this as a mathematical model for a holographic image. Basically, for each point in a 3D space, X, Y, Z, we have the flux or radiance energy that comes from all directions. And so this parameterized on the sphere, so by angles theta and phi, right? And this depends on time. So the plein-optic function is a function that has dimension. The domain is the phase space, a 6D phase space is the ambient space, R3, the sphere, S2, and time, R. And this returns this radiant energy. So it's a spectral radiation. And so this completely describes all the visual information that exists in the world. And you see this as a volumetric description. Here, we are not talking about explicit geometry, surface, or objects. It's basically the whole space and how radiance energy exists in the ambient space, right? And then from that, we are going to capture those rays that actually carry radiance energy. And so actually what we are going to capture is a light field. A light field is a slice of the plein-optic function. So basically is a structured sampling of the plein-optic function. So we are going to sample rays from all this radiance energy that is around there, and many rays. So, but we are going to select the rays that we want to sample, so to create a mathematical model. And so for that, we need to understand the dimension of a light field. So a light field could be two-dimensional, three-dimensional, or four-dimensional. So we'll see that how this relates to cameras, right? So a 2D light field actually is this what's captured by a simple camera or even a more sophisticated camera. We have discussed here the geometry of the pinhole camera. So pinhole camera captures rays in a very constrained manner, right? So it's a box with a hole and a sensor, right? And so basically the hole is a point, so has topological dimension 0, right? And then the sensor is a region of a plane, so has topological dimension 2. So the dimension of a light ray, that is associated with a pinhole camera is 2, because 0D plus 2D, right? And actually has a limited field of view because the way the system works, captures only the rays that arrive at the image plane, and that's constrained by the viewing angle of the camera, right? But then we have a more general camera that is an omnidirectional camera. So basically, the omnidirectional camera is the most complete 2D camera because basically captures all rays that are incident at single points. And if we refer to this image here, each point in space, receives lights for all directions. So omnidirectional image captures all the lights that comes at a single point. And this is really important because for us, if you are sitting in a position and looking around, so then all the environment is around you. And if you take an image with this omnidirectional camera, you have all this, and then you can, look around and select this and see the environment around that point of the center of interest, right? But then we have, but notice that here we don't have depth information, right? Because we just have the rays arriving at a single point, right? But if you want to have depth information, we need to have disparity. And then you have like a stereo cameras that have the sense of depth. So basically, we do line sampling. One way to create like a 3D stereo panorama is to put cameras around a circle. And then, because you have many cameras, then you can reconstruct a stereo 360-degree image. You could also put cameras along a line and then get a stereo, but not 360 degree. But the point here is that if you put many cameras with different points of view varying in 1D, then you have a 3D light field, because the cameras capture angles, rays, and collect this rays in a 2D plane, and then you have many cameras along a line. So the dimensions is 3D. And some examples of this stereo 3D panoramas are the Google Jump camera and the Facebook 360 surround camera. So these are special types of camera that you can compute a representation that you can use for 3D stereo VR. You put the glasses and you see a 3D stereo image. And it's very convincing. But finally, we have the full 4D light field. So this is a more complete sampling of the plein function, because this light field actually captures, the rays in a volume of space, right? And so the idea is that you have some surface, could be a plane or some other surface, and then you put several cameras, in occupying this, area of this surface. And so then you have a sampling based on 2D domain, and the rays are also 2D. So you have a full light field because it's 2D plus 2D. And one example of this is the LITRO camera. So the LITRO camera basically is an array of cameras, right? And this, some of this work was developed at Stanford. We are going to see this further in the lecture. And there's a nice way to represent 4D light field is that the two-plane parameterization, because we take like the subset of the parameters U and V as the position of the cameras in this array. And then the rays in each image, we can take like S and T, and then there's other parameters. So notice that is a function that's a 4D function, right? And this is the full dimensional light field camera, right? And one example of this is this experimental camera that was developed at Stanford, and also the LITRO camera, that is a camera that was developed by a PhD student of Stanford that did this startup that is LITRO, and further on was acquired by Google. All right. Okay. Now we are going to talk about cameras and lenses, because all these types of cameras are models that capture this set of rays, and for that they need some optics, and you see the need for optics, how that goes into the picture. And we are going to discuss cameras in general and what makes them work, this system of optics and lenses. All right. So we are going to start discussing the principles of lens design and motivating the needs for optics and lenses in a camera. And we are going to discuss the geometric optics of a pinhole camera, associating, the mathematical model of a pinhole camera with the real camera that was a system of lenses to simulate the effect of a pinhole, but with many practical advantages. And so we are going to study simple lenses that actually is a good optical model for the complete lens. That is a lens system with many components. And that will be enough for us to do all the math and the mathematical model for that. Okay, so why we need lenses? We couldn't use just the sensors and have just the sensors and no need for optics. We have the rays, coming, in all the directions, and then just collect the rays. Well, the problem is that, this light rays comes from all directions, and we couldn't make sense, because actually, as I was telling before, we need structured sampling. We need to, figure out which rays come from which directions, and how we are going to organize them to make computations, to have our representations, right? And so in that way, we need a way to be more selective, to get the rays from certain directions, identify them, and have as parameters of our model, right? And for this, we are going to use lenses, right? So we need to be more selective, right? But we talked here in the course about a pinhole camera, right? A pinhole camera is a nice way to be selective about rays, because we have just in the ideal mathematical world, infinitesimal points, and the rays can only go through that point, right? So, and then you can see here that a ray that comes through the pinhole is the center of the optics, right? From all rays go through that and reach the sensor. And so we know exactly the direction of the ray, because for a point in the sensor, And the pinhole, we have a direction of the ray. And so we have the ray, and then we can do all the math, right? But in practice, real cameras don't have this infinitesimal hole. We have like a real pinhole, and a pinhole is an aperture that has a size, right? And so if you have like a very small pinhole, we direct the rays very nicely to the sensor, and we have a sharp image. But if you have a hole that is a little bit larger, right? These rays are going to mix up and reach the sensor, and going to be integrated into a blur and have a fuzzy image. And we don't want that, right? And so how to determine the right size of this hole for a real pinhole camera? We have to now go into another effect that is related to electromagnetism and the way the nature of light, because radiant energy comes from light, and the mathematical model of light has a dual aspect, because on one hand is corpuscular because carries photons that are light energy, but on the other hand, these photons vibrate, and so we have an undulatory model. And so light has a wave nature. We have electromagnetic waves for light, right? And then we have these principles of diffraction, because if you have an aperture, and as you make the aperture smaller and smaller, you start to get diffraction. And another mathematical interpretation of this is that if we take this information from the spatial domain and transform it to the spectral domain, do a Fourier transform of this aperture, the smaller the aperture, you have a bigger Fourier spectrum, more frequency. And this sort of like relates to the fact that we are carrying information that to have higher frequencies, and we have like a sharpness as we make the aperture smaller and smaller. You get the image sharper and sharper, but there's a limit, and the limit is related to the phenomenon of the diffraction. And so the bottom line is this: the smaller the hole, more diffraction you get. But you don't want to interfere with the ways that the light energy are propagating, this undulatory behavior of the rays. So if you make the hole very small, the aperture very small, you are going to have the diffraction that's going to bend the rays in a way that is not desirable, right? And what happens is this: if you take a hole that's large, you get a blurry image, and you start like making the hole smaller and smaller and smaller, you get the image sharper and sharper and sharper. This is the image of a filament of a light bulb, right? So in the first image, you can barely see the filament, right? In the second image, the B, you can see the shape of the filament, right? So this is the right size for the aperture. But then if you make the aperture smaller yet, then we start to getting blurry and blurrier. And there's some points that is the aperture is going to be so small that you couldn't barely capture any light, right? Because we are not talking about like a ideal mathematical model that just one ray can pass through that very small aperture, right? Because the rays, like there's are photons that are bouncing around, like vibrating, and so there are many phenomena that happen at this microscopic scale. So that's related to the wave nature of light, right? And so the point is that can reduce this hole up to a certain point to get a sharp image. But then after that, you start actually to getting a blurry image because the rays go to different directions, and then you start to getting blurriness, as shown in this example, right? So what's the solution? Because we have two problems when we use a pinhole without lenses, right? The first problem is that as we make the hole smaller and smaller, we capture less and less light. And the sensor needs to capture a certain amount of photons to get an accurate reading, because basically the sensor is counting photons, the number of photons that arrive per certain interval of time, right? So a very small pinhole, is not going to capture enough light. On the other hand, as we make the hole smaller, we get less light, and if you make it smaller than that, we don't have sharpness because of diffractions. And so what is the solution? Is to use another principle of optics that's, instead of diffraction, we are going to use refraction. And refraction comes from lenses, right? And then that's why we need lenses in our cameras, right? And what are the goods that the lenses can do to us? First, lenses gather much more light because basically I can have like a very large aperture in a lens, and the rays come, through that aperture, through the lenses, and you can figure out, depending on the optical system of the lens, how the light paths, cross the lenses, and figure out this in our sensors, right? And so they carry more light, and because of that, we can capture the images, in the right time, because we need to, in the sensor, we need to read the number of photons. And if you have things that are moving fast in the world, we need to basically take a snapshot and in a very short interval of time. And if you have a lens that has a large aperture, we are going to capture enough light to have a very short exposure time. So this is a comparison. We have a simulation of a pinhole camera with a very small aperture, and we need like 60 seconds to get the top image with the right exposure. But then if you have a regular lens with aperture of f16, and then we have an exposure time of 100 of a second. So, and that's enough to capture in movements, just to freeze the movement of slow moving objects. And if we have lenses with larger aperture, we could capture like a sports, or in racing cars, just a car, to freeze the motion, right? So this is the good for the lenses, and also the optical characteristics of the lenses allows us to figure out the light paths and see how the lenses are directing the rays, and which rays are the rays that we are going to put in our representation to the sensor, right? But there's one other aspect, that because the lens needs to be focused, and because of the way the system works, we have to take that into account. And so I'm going to discuss now what focus is, right? Basically, in the top image, you see like you have like a pinhole, and we see the path of the rays. They're very simple because they pass only through a point and go to the sensor. But when you have a lens, you have a large aperture, and the rays goes to different parts of the lens. The rays goes to the center, to the top, And then if you have an object at certain distance, the rays from a point at that distance are going to kind of go through the lenses and are going to be focused on a certain point depending on the kind of lenses. And basically, we basically need to align the information, to focus the point distances, planes in the space, distance from the camera. So we have sharpness. So the bottom line is that when you use a lenses, there is one area in the environment that is very sharp because all the rays are, converge to the right points. A ray from the same point there, if the focus is correct, they are all going to arrive in the same point in the sensor. But if you have an object that is farther than that point, the rays are not going to converge and they're going to be very blurry. So, in 3D, some objects at a certain distance are going to be in focus and some are going to be out of focus. And then you can change the focus to compensate for that. So basically, we do like this shift to align, the rays to the right point and work with the focusing. And this alignment is based on a focus plane, and that's the focus plane is related to the focal distance of the lens system, right? Okay, so the way it works is like this. We start with a pinhole model of the camera, and so we have at a certain distance that we are going to call the focal distance, we have our sensor, right? And then this is for the ideal model of a pinhole camera. But when you put a lens, what happens is that we can sort of a model, the simplest model of a real lens. We are going to use the model of a thin lens, and the optics of a thin lens is a simplification of geometrical optics of well-behaved lens systems that we actually use in our cameras, right? And this, we have two phenomena. One, that the rays that go through the center of the lens, they are not deviate. They just go to the center of the lens, the same way as we have this in a pinhole camera. But the rays that are parallel to the camera, to the lens, they focus on a plane that is located exactly at the focal length, right? And if we combine these two things, we will have a way to control the focus, right? So the idea is that imagine you have an object as a distance d, right? And then what we want is that the rays that come from that point in this object at distance d, the rays that are going to pass through the lens and the center of the lens, they are going to arrive at the point in the image plane. And we want all the rays that go parallel to the lens. They have to arrive at the same point. And this is exactly how we focus. It's just changing the focus distance so that all the rays that come from that plane are going to be combined in the very sharp corresponding point at the sensor. And then as we move, this, the focus back and forth, we are going to focus at objects at different distances, right? There's some other things that I'm going to discuss here is that you have like called depth of field. I'm saying that the rays that are exactly at that plane, they are in focus, in perfect focus. But in practice, in a real, camera with a real lens, we have what's called depth of field, because, we consider that distance, that plane, and two parallel planes, and the points that are behind or in front of these parallel planes, they also in focus, but not in a very sharp focus. And there are many things that we can consider, including the size of the aperture and other things that affect the depth of field. But basically, the mathematics for this thin optics lens is using these two properties that we can control to do focus. And then to do focus, basically, we move the sensor, based on the focal length of the system, right? And then we get the images we want, right? Because usually when you take a picture, there's something at some certain distance that's of interest, right? And then you focus there, and the rest may be blurry, and then this actually, in some cases, is desirable. All right. So now that we understood the lenses, we are going to see how we put this into camera systems. And then from that, we are going to design cameras that are going to actually create light fields, collect the rays, right? And so we are going to concentrate on the acquisition of a 4D light field. And then we are going to discuss also simpler light fields, 3D and 2D light fields. And so the idea is like twofold. First, we want to capture the 4D light field. And then we want to have a representation. How do we represent a light field? A mathematical representation that we can manipulate, right? Okay, and the idea is that we are not going to, imagine a simple camera with a simple lens system, because exactly the problem of the focusing, right? Because focusing the focus in a regular camera, what happens is that for each point in the sensor, actually, in a sensor element that corresponds to a pixel, there is an area. In that area, we are integrating all the light rays that come over there, and then you get the average reading of the number of photons per interval of time. That's the exposure time, right? And what happens is that all the lights that come through those rays are integrated at that pixel, and and this is also related to focus, right? And so the idea is that we want to capture a light field, we want actually to capture the rays, not the pixels, right? And then we can design a sensing element that's going to actually discriminate the rays in a more precise manner. And so this is the idea of the panoptic cameras that capture a full light field. I was saying before that one way to have a 4D light field camera is to put a lot of regular cameras in an array and then capture several images. And then from that, you create the representation, because you have, a 2D space of cameras, and then you have a 2D space of rays, then you have a 4D light field. But there's a very ingenious way to do a 4D light field camera using optics, because basically we want to record this 4D set of rays, right? And so basically we have two sets of lens. One is the main lens of the camera, so like a big lens in front of the camera. But then in the sensor, we put like micro lens, like tiny lens that you could imagine that corresponds to a super pixel, right? And so under this micro lens, we have a small array of sensors, right? And then considering the coupling between these two optics, we can figure out the directions of rays that go through the big lens and the small lens and arrive at those sensing elements. And in that way, we get a 4D light field. And this, the idea of a full field light field has actually evolved through time, right? Because the first idealized model for a 4D light field was done by Lippmann in the beginning of the past century, in 1908, right? But this was just the idea, not a realization. And then in 1992, Adsel and Wang, they designed the first planoptic camera, but with design that was saying an array of cameras, right? And this design that I mentioned using micro lens is basically a special camera with this micro lens array in front of the sensor that was part of the PhD of this Stanford student that actually created that company Litro, right? And this is made practical to have, full field light field cameras, as a consumer product, right? They designed different types of planoptic cameras for consumer, practitioners, and also for professionals in film and things like that, right? And so let's understand how we can represent a 4D light field that's captured from one of those cameras. The idea that we want to capture all the rays that are reaching the lens and arrive at the sensor. So we have like 2D for the lens aperture and 2D for the focal plane. And by that, we discriminate which rays come from which directions, and we can put in our representations. But there is a dual interpretation of this, because if you think about the conjugate of the camera, we have the lens aperture and the rays that goes to the lens aperture, and then you have the rays that arrive at the sensor. And so that's more or less a kind of symmetrical situation from here, right? So we have this and you have that, right? And imagining this, we can kind of go and analyze the relation between the sensor and the focal plane, and imagine this parametrization that's called two-plane parametrization, because we have the rays that are related to the aperture, and the rays that are related to the sensor and the image plane, they're the same, right? So, and basically we have this, U and V corresponds to, points in the sensor, and S and T to directions, or vice versa, right? And as I mentioned before, this is a 4D representation, and basically describes all the rays that we are collecting, right? And how do we understand this? Exactly what I'm saying. I mean, you can imagine that if you have constant UV, that would be like a lot of pinhole images at different aperture points, like exactly the same as having an array of cameras, right? And then if you have a constant SNT or XY, right? Then this is for a point, certain point, all the rays that arrive at that point, right? In this takes into account, including the variation of the focal plane that depends on angle, right? And so here's a visualization that's easy to understand. So if we consider the UV plane, and a point in UV plane, describes, each point describes an image, because we keep UV fixed and very SNT. And so we have, basically an image from a regular camera. But then if you take this fixed ST point and takes all UV points, you are seeing different areas that come at different angles. So basically, this is the radiance that comes from the hemisphere on this point. And you can relate this with what I say with the microarray, right? Because it's like, in this S and T would be related to that microarray of lenses, right? And then if we do the dual, we get like the UV, right? And actually, we have a way to have a full visualization of this, because if instead we fix a point, we could fix a direction, and then we could have a slice of this 4D, a space. That's a slice of 4D space is three-dimensional, right? And here you see, like you have, like we are varying S, U, and V, and T is fixed, right? And then we see how this rays kind of evolve. Okay, but there is one catch, because in the end, what we want to do is do a view resynthesis, because we have individual rays, but we wanted to have a continuous representation. Here we have a discrete representation, because it is a sampling, right? And then to get this continuous representation, to get rays at any point in this space of rays, we need to do resampling. And so basically, resampling is like interpolation of the information about these rays, right? And this is something that has to be done in a very careful way. Like here you see, like you have, let's say you want to get a ray that is between 2 pixels, right? I have to interpolate the information of the pixels around that to get that ray in a continuous manner, right? So basically it's reconstruction, but it's reconstruction and resampling. And for that, we have to consider the rays from a certain viewpoint to a pixel, and we compute the intersection of the rays with these 2 planes. And then we are going to look at the visual information, the RGB light energy at S, T, U, and V, and do this interpolation process. But what happens that this, I mentioned before, that this plein function doesn't consider the geometry of the scene, right? And if you consider the geometry of the scene, there is occlusion, because if you have an object here, and then you have something here, if you are there, that object is blocking the rays that come from the parts that are behind the object. And if you are carrying, rays that, vary, the position relative to that object, you cannot interpolate all the rays. You can interpolate only the rays that are in a continuous surface. When you have that depth discontinuity, we cannot do that. And that's the reason that when you use light fields, we have to be very careful. And when you get extra information, like depth information, we can do this reconstruction in a much better way. And actually, this is one of the reasons that neural methods for neural radiance fields work better, because they capture the plein function, but also they capture this volumetric information, the density of matter in the space. So this geometric information, right? I'm going to talk about this later. So now I'm going to show some results of doing this and working with light fields, right? So this is the original work of Stanford, and they have a big database of this light fields. And so they had a previous one, and this is a newer one, but it's also has sometimes, it's the light field archive. And here you have a lot of light fields that they generate based on different equipments, right? So these ones were generated by either from a digital model or this, array of cameras, right? And this is the famous Stanford Benny. And here you see for each, data sets, they have the original camera lens, the rectified images, the light field and everything, right? And then these light fields that come from a microscope that are very useful in science. So we have different light fields that come from a microscope. And these light fields that come from a special gantry that was used to capture materials, right? And these are more light fields from the camera array, right? And so we can play with these light fields. So to play with these light fields, I'm going to show this, a light field viewer that works better in a browser. So see this light field viewer. Let me put. Here we have this dragon. We can see that from the side or in front. It actually is loading, and you see here there is a lens, and then we see the effects of the rays that go through the lens in 3D space. I'm going to start with the dragon on the sides, and then here, if I click on a point, it's going to focus on that point, right? And so if I click here in the front, because it simulates a real camera with the focus, right? So some parts are going to be in focus, some parts are going to be out of focus, right? So if I click like in the very back, so everything is blurred, but the back is sharp. So click in front, the front sharp, and this is a little bit out of focus, but it's okay, right? And this depends on the aperture. And so like if I make the aperture very big, then this focusing effect is going to be much stronger, right? So see, it's very out of focus, right? So if I make the aperture very small, it's going to be in focus because it's almost like a pinhole camera, right? And then, I can also vary the focus continuously, like a different, right? And this effect actually is more pronounced when you look at this into this dragon scene from the front with the lens, because we have more depth, right? So if I click right here, here is in focus and here is very out of focus. And if I make the aperture even bigger, this is going to be much more pronounced. You see, like, look at the tail of the dragon. And as I move, it gets sharper and sharper because I'm making the aperture smaller, right? And actually you can see what happens to this lens, because if I click in this lens, the lens itself is in focus, right? But, the rays that arrive here, are not in the surface of the lens. They come from the back. So they are more, in better focus, but not total focus, right? And you see, like here, you can really see, right? Because the lens is in front, you can see the effect, right? On the other hand, if I click here, the lens is totally out of focus. And there are many things that we can play with light fields, because basically we can do 3D reconstruction with these 4D light fields. Right? And now I'm going to change gears and discuss 2D light fields, but the full 360 2D light fields, omnidirectional light fields, because these are very practical. Because in graphics, sometimes you want to capture, the environment. Like in games, you have like this skybox, And the ideal to do this is to use a 360-degree camera, right? And also, if you use like a 3D light field, a stereo 360-degree image, you can use this for VR, for stereo VR, movies to see in a mobile or to see in a headset. And so basically, as I mentioned, the omnidirectional image is the set of all rays that are incident in a point in space. So we call this a spherical light field. And so the mathematical model, this is actually the rays that arrive at a single point and can be represents at points in the sphere or directions associated with the unit sphere, right? And then to capture these spherical light fields, we have different types of the actual cameras. We have catadioptric cameras, dioptric cameras, and multi-cameras. Basically, the catadioptric cameras are parabolic mirrors that bend the rays and kind of they get like a 180 field of view, right? And then you have dioptric lens that they basically have a fisheye lens and have almost 180 field of view. And then you can have also multi-camera, but in this way, we put the cameras on the surface of a sphere, and then we get like a 360-degree field of view. And depending how you do it, you could get like a stereo and 3D light fields with depth also, right? So the professional cameras for 3D VR are like of this type, right? But then we also need to discuss the representation of these spherical light fields. Basically, there are 4 different image formats for omnidirectional panoramas, and they are related to different parameterizations of the sphere. We have the lat-long, cube map, azimuthal, and stereograph. So the lat-long representation is basically a parameterization of the angles, latitude and longitude. And but what is done is like you have the latitude going from 0 to 360 degrees, and the longitude going from minus 90 to 90, right? So we have the angles around and along, right? But then you map these angles in a image, a rectangular image, and that's very convenient because you have just an image, right? But you have to interpret these images. The pixels are actually rays, and there's a sampling thing because, like around the equator, you have the full resolution, right? But then at the top and the bottom, these are the poles of the sphere, right? And so this line on the top and this line on the bottom, these are the North Pole and the South Pole, just a single point. And so basically the resolution kind of gets, changed, right? And so I have this distortion. But this is the most convenient format for archiving. And actually, there's a big group on Flickr for people that take 360-degree images, and there's a good source of data for machine learning, things like that, right? And then you have cube mapping that is ideal for digital representations, because if you have a system like a Blender or Unity, or basically you have your scene and you create these virtual cameras, each one associates with the face of a cube, and then you have all the rays in a nice way, and there's no problem with this issue of the distortion because of the singularities of the poles. But you have to kind of do the continuity, because the cube is topologically equivalent to the sphere, but you have like these seams where the face of the cube meets the edges of the cube, right? But this is very useful for CG rendering. And then you have like this azimuthal projection. Basically, you project the top and the bottom hemispheres of the sphere in two disks. And this actually is the standard that's used for planetariums, for projection in the planetarium, right? And also, I don't need to say that there are conversions between all these representations, and you can convert back and forth without any problem. And then there is the stereographic projection that's actually the best representation for computation, because basically it's a conformal mapping, and it's basically based on a stereographic projection, and is associated with operations in the complex plane, right? And this is a very rich source of, tools to manipulate 360-degree images, right? And then the same way I was saying that for a 4D light field, it's good to have geometry, for omnidirectional images and actually normal images. If we have geometry, we have more information, because we know a long array. If you have the depth, if you know which point in the scene corresponds to information coming from that ray, then you have geometry information. So RGBD, the depth associated with each ray, is a very important information. And then I want to show this project. It's expanded panoramas. Is a student of mine, a PhD student that work on these extended panoramas. And this is part of his PhD thesis. He finished a while ago. But the idea is that you can structure things in a very nice way, because this, you see, is a 360 image in an equirectangular format, right? But then we can structure, like, we segment the objects because we have depth, right? And then you have the full depth of everything. And so we have the background, and then we have the individual objects separate. And then you can associate them with virtual or real objects. You can include real objects, and include illumination, other things, and then you can reconstruct this in 3D. And so this is what we can do if you have this extended panorama. Like, you can look around, and if you combine those, you have information that is similar to have representation with 4D light fields, or the newer models that consider machine learning and nerves and Gaussian splatting and etc. Right? Okay, so now time for a break. Okay, so now in the second part of the lecture, we are going to discuss image collections. And image collections is something that we are just talking about, time varying, capture of images. So you can imagine image collection as something that's more general. And basically, you get images that have something in common. And so this is an image collection. And from that, to understand what is in common about this collection of images, we can create a mathematical model and exploit this for machine learning. So that's the idea of this second part of the lecture. Okay, so what we are going to discuss is, like, first a motivation to have like image collections, then give a historical perspective, how this idea evolved and how it was applied in computer science and applications. And then I'm going to introduce a conceptual framework that we developed at IMPA to understand the image collections and work with that for computational photography and machine learning. So we are going to talk about the main mathematical tools associated with dealing with image collections, the basic computational techniques, and the relations with deep learning that we are going to use like in the rest of the course. Okay. So to start, I would like to show this teaser and ask this question: what do these two images have in common? Yeah, but that's the trivial answer. The non-trivial answer, besides being two images, because this is actually in the description, what they have in common. They are production of image collections. Why? Because they were generating from many images, but generating different ways, because this is actually a group portrait that combines the information of several images taken one right after the other, right? And actually in your cell phone, in your smartphone, if it's a iOS phone, iPhone or iPad, the camera actually has the live photo. This comes from a live photo because it takes one image after the other. And why this is good? Because let's say you are like in a birthday party or something, right? So everybody around the table, and the photographer says, cheese, and people show their best faces at different moments. And usually, if you have a group like this, a large group, you are not going to be able to get the best image of each face in one single image, one single instant. But in that time interval, everybody positions themselves and make a smile, and then you can get the best for each person. And then you sort of segment the image in different parts, and then you combine them in a perfect, ideal picture that everybody is happy, everybody is laughing, and this is something that is ideal. It would be impossible to get like with a normal camera, right? And this is something different. This is a medical illustration, and this is a bone, and you want to get a very precise silhouette of the bone. And it's difficult to understand the silhouettes from just one image. And so this was taken from a camera with 4 flashes, one shining from top, another shining from bottom, and from two sides. And so this illumination, they change, you know, the way lights reach the object, and makes it easier to capture the silhouettes. And then you combine the silhouettes of an average of the information, and then you get this very nice representation of this bone, right? So these are the 2 different applications of image collections, right? And this, as I mentioned, is a recent trend that actually combines 2 different areas and technologies, you know, something that is like an innovation that changes media. It's a new type of media. So in one hand, it's associated with computational photography and video, something that we discussed in the first part of the lecture. And then it also combines the convergence of areas that's called image-based modeling and rendering, because it's actually, you know, taking advantage of analysis and synthesis of images in the context of AI graphics, right? And so what are our goals here? First is to elaborate on the basic concepts behind image collections, then studied a related mathematical and computational theory that makes sense of these concepts and understands the main techniques that are used associated with image collections, and see the emerging applications that come with this new media, and also prospectively identify the lines of research that are going to get more innovation in the future, including machine learning. Okay, so to understand image collections, we need to make some defining questions. The first one is, what are image collections, right? The second one is, why do you need them, right? And if we need them, we need them for some purpose. So what is that purpose? How to make interesting things with the image collections? And if you answer all these three questions, we are going to have to study the mathematical tools, computational techniques, and the areas of applications of image collections, right? Okay, going step by step. What are image collections? My definition of image collection is the set of images IK with the following properties. One, it shares an affinity relation A. Two, they are all mapped to a common support U. And they also have an underlying attribute model M. And if you think about it, this is very related to the concept that is described in the very beginning of the course of a media object. Because a media object has a common support, an attribute model, and when you make several media objects that are all images and create an image collection, they have this affinity relation, right? And so this is a new kind of object because it's a sort of an intermediate media type. Because it's not an image, it's not a video. It's an image collection. So it's a more general beast. So it's forward-looking. You are thinking about innovation in the future, right? And so to understand this, we have first concentrate on the affinity relation. What is affinity relation? Affinity relation is what I'm calling coherence binding. It's something that makes sense of all those images. They have something in common. And what they could have in common? Many different things depending on the kind of collection you have. It could be a spatial coherence, so images that are taken from the same position, or temporal positions, have many cameras, different positions, but all taken at the same time, or images of the same subject, the same person that every day takes a picture when the person wakes up. And then you can exploit this fact to do things with these collections, right? And usually in the context of computational photography, they are guaranteed by construction because in the acquisition setup, we have a computational camera that guarantees that they're all taken at the same time. Let's say you have an iPhone and takes a lot of pictures one after the other. And so they are all at the same time. Or illumination, you have a camera with several flashes and shines from different ways, one at a time. And then this, is done. And you know that, your image collection has that property. But to create new media and do different things, we have to understand what we want to do with them, right? And so, and also understands that are not necessarily an image, can be a different type of media. Could be like a 2.5D sequence, could be a 3-dimensional object, could be an image that comes from several images. And for that, we need to do analysis and synthesis, right? And this we have there's two other aspects. We need to have a common support U for all these images in the collection, and we need to have an underlying mathematical model that exploits the affinity relation, right? And if you think about this, and in the hindsight analyzing this historically, this actually is a generalization in computer vision, because in computer vision we have this problem that's called shape from X, right? And then if you generalize this, we have something that is not just shaped, it's anything for anything, Y from X. And this is a generalization of the problem in traditional computer vision, right? So to really understand this, let's delve into the problem of shape from X. Because basically, depending on this X, could be shape from stereo, shape from shading, shape from the focus, shape from texture, etc. Right? And basically, in computer vision, this is a problem of inference from a known model. But this model is a parametric because when you want to do like shape and you what you are going to compute shape from, you have a mathematical model that's parametric, and you want to infer the parameters of that model, right? But in this new setting of image collections, y from x, x is a general image collection, and y is a general media object. And then we are going to extract a general media object from an image collection. And this, the difference that we are going to do inference from a non-parametric model. And this makes this image-based, because the non-parametric is that you have the image collection. And then we are going to exploit the affinity relation. We're going to exploit the control variation that has into this image collection in the affinity relation. And to really understand the difference, let's see a concrete example, an example of normal computation from different photographs, right? In the vision context, the traditional vision shape from shading, right? We have the shading model, and we are going to compute the shape based on shading, right? And in image-based approach, we are going to actually do photometric reconstruction from the images in a constraint set. So shape from shading, basically, we have this Lambertian model. We first assume that the surfaces in a scene, they are all diffuse. And so the shading model is a Lambertian model that's given by this equation. So basically, you have an object, you have the light, and have the viewer, and the shading depends on the cosine of this angle theta between the normal of the object and the light ray that comes from the light. And then you have this view ray, and based on that, you have to do this. And since this is a kind of an ideal model, it's not very accurate in practice, because objects are not perfect diffuse reflectors, right? Some objects are more and some others are not. Like the mouse, is very reflective, and the chalk is very diffuse. And so this would be good for very diffuse materials. But even like that, you have to make some simplifying assumptions. First, you assume that the reflectance is constant. Like this rho is a 1, to make things simpler, right? Then, because you have to integrate this, you have to assume some continuity and smoothness across the surface. And then you also have to assume some boundary conditions, because what happens is that if you have discontinuities, you have the normal value with a smooth variation across the surface, then at the boundaries, the edges, there's a discontinuity. And this is very difficult to compute in practice, right? But if you look at the visual literature, there are tons of papers in shape from shading, right? But what I'm saying is that the image collection approach is much more effective. And so the image collection approach is basically photometric reconstruction. We are going to constrain in the capture an image collection. The idea is that we have a camera and the object fixed. So have an object here, have a camera, this is fixed, now we're going to change. But I'm going to change the illumination, because this equation here is based on illumination, right? So I'm going to change the illumination. And so I have controlled variation, right? And then I first put a light here, and then have this equation that its equation is basically that equation that I saw there written in a different form. But the position of light at point 1. Then I have light in the point 2, and I have the other equation, right? And then a third, and then with this is enough for me to compute the normals, right? Because basically I have this linear system, right? And what I want to compute is the normal, right? That's in here. It's the same, just one normal, right? But then I have like this parameters, different light positions at different intensities. And this is the reflectance, right? That rho, right? And so basically I invert this, and then I get my normal, right? And then I normalize this and assume like I compute the albedo also, right? So this is really effective and teaches a very nice lesson that we need controlled variation. You see that in that example, only one parameter is varied. All the others are constant. And this is enough for us to put together that linear system and compute the normals in a very robust way, right? But this applies to many other examples, because depending on what we are varying or to keep constant, we can do different applications. There was light that we are varying. So, but you can vary the scene, the exposure, the view angle, the subject, the movement, the point of view, and other things, right? So I'm going to give all the examples for that. Like in the case of the scene, we can do a difficult problem. That's the foreground, background decomposition. Because basically, we take two images, one of the background, another the scene with someone that's not in the background. And then we just subtract one from the other, and we have like a segmentation, right? And this is very easy, because you put a camera there and take a picture, and then when someone appears, you take another picture, and that's done, right? The same for exposure, because usually in our cameras, the sensor has a small dynamic range. You cannot capture the full variation of incoming light. Like, let's say if you take a picture in the outside with the bright sunlight in a shadow, the sensor cannot measure the radiant energy with all that range. And so then we have the concept of high dynamic range image. Basically, you have same scene with different exposure. And you have this in your phone, right? Compute HDR, right? Basically, it takes a lot of pictures with different exposures. And then here you can see the highlight very clearly. And here you see barely some parts that are very dark, and here you cannot even distinguish. When you incorporate this, you actually compute the radiance energy with high dynamic range, right? And then you have panoramas. Panorama is a kind of 360-degree image, but more generalized. So have the same viewpoint with different orientation. And then basically we can glue this together and make a very wide image. And this is also having your iPhone. All these things that I'm discussing, come from computational photography, and most of them were implemented in products like a smartphone and things like that, right? And then there are other things that are actually using in machine learning, like a subject. Like if you have photos of the same person with different expressions, you can understand how that person, express emotion, how the person talks, and things like that, right? And also for movement, because you have the same objects with different poses instead of expressions, and then you can do tracking and you do motion capture, right? And finally, something that we are going to use a lot in this course in the future is changing the point of view. It's stereo multi-view reconstruction. And we already talked a little bit about this in the previous lecture, right? Because we have the same scene with different cameras. So we have parallax, so we capture the same from this point and that point, and you want to compute this 3D point in space based on information on the two images. Basically, this is a way to compute that information. And actually, is one way that we have a 3D light field, a stereo 3D camera, is done in this manner, right? Okay. Now that we have seen a lot of interesting applications, how do we implement that? How to create, those things based on this control variation? Well, we have to solve 5 problems. At least, right? You have to solve a problem of registration, segmentation, model estimation, fusion, and resynthesis. Because solving this problem are going to guarantee those properties that we discussed, that we need a common support, and we did underlying mathematical model. And then that's related to the affinity binding and to the application. And there are actually two approaches for solving this problem. One is the classic approach, and now we have like machine learning, deep learning, to do this in a much better way, right? And so the first problem is registration, because basically we need to have all the images in the image collection corresponding one to the other, or the things that matter have to correspond, right? And then there are many techniques. The traditional techniques are like coarse or dense registration. So the coarse approach is like you do feature detection, and then you relate, this feature with that feature, and then you can, register one with the other, right? You can also do like some pattern matching, and then you can register. And also you have this dense method, because if the distance between things are not very far, you can use optical flow and basically kind of warp one image into another in a very nice way. Then you have segmentation. Segmentation, there's a lot of progress in this area in machine learning, and there's a classical problem, in vision. And basically, you have two principles for segmentation. One is edge-based. You detect the edge, of the objects, and then you know the interior. And the other is the opposite. You detect the patterns in the interior, and then from that you compute the boundary. And this is related to create a mask to actually separate one from the other. And notice that segmentation is related to detecting things like a registration, things like that, right? And then you can also do tracking things, combining these two things. And then you have model estimation, and there are different mathematical models that you can exploit, right? When I was discussing, this photometric reconstruction, I showed like a linear system. So you can have like a multilinear system, a Bayesian probabilistic model, a perceptual model, projected model that takes into account, the geometry and the cameras. And this now is really powered by machine learning. So the model estimation now benefits from the techniques of deep learning associated with AI graphics. And then you have fusion, because you have many images in the image collection, and based on those computations, you want to combine them in different ways. And there are many techniques to combine. They are basically, you can blend them together, you can compose them together, you can reconstruct, and that is related to what we are going to do, right? So this is a simple example. And then you have resynthesis, because once you have some underlying mathematical model, you can actually do a generative process, right? Because this model can be like a stochastic, be like a noise-based model, or spectral, we are manipulating the frequencies, or a pattern, you are manipulating the structure. But basically, all these models, using deep learning, machine learning, we can estimate a generative model that are going to create things based on features, right? That come from the image collection. So, with that, some remarks. I list like these 5 important operations and problems to solve, but some of these operations may be trivial depending on the kind of application. Like registration. Imagine that I have a static camera and a static object. Everything is registered. I don't need to do anything. I know because I put my setup that way, right? Also, segmentation. If I have a neutral background, I don't need to do any segmentation. This actually is a technique that's used for special effects. They call like a green screen. So they have a screen that screens the background, and everything that's not green is the object that you want to. Obviously, they pick green because it's something that doesn't appear in humans. Maybe in an extraterrestrial person, but not in humans. And those you can use this in TV for news and other shows, right? And then modeling, you can actually have your model, right, beforehand, and impose your model in the image collection. So it could be given. or fusion can be something trivial. Just for some applications, may just combine the things together. And resynthesis actually don't need to do resynthesis all the time. So some applications that will be like a no operation. So in some of these things, the operation will be trivial, like identity, and some others will be like something that's not going to be there, right? And now, just to finalize, what are the tools that we are going to use to solve those problems? First, we need like visual computing tools. So for image processing, how to format the data, we are going to use computational geometry to create structures, graph theory to create relations between things, elements, and mathematical tools, especially related to modeling, right? We are going to use probability because we have an affinity relation, and then we are going to analyze the statistics and common aspects of the data, right? And we are going to do parameter estimations using the statistics. And to really apply this, you want to get the best solutions. And so we are going to use optimizations in the form of minimal energy functions. And this fits very well into the deep learning and machine learning approach, right? And especially these energy functionals, because basically are functions that are going to minimize some energy associated with the model, right? And we are going to see here further that we can take advantage of the Bayesian models because the Bayesian model exploits some a priori knowledge. So in machine learning, you also say, I need a prior, I have a prior for this and that, right? And so the Bayesian probabilistic approach associated with machine learning going to lead to good energy functionals that we are going to optimize and have the best models. And finally, as I was saying, I mean, like, when you use deep learning, sometimes we can get the image collection from capture, but sometimes we can like do a curatorship and have the data, analyze the data, and separate the data in a certain way that we create the image collection in the process of the machine learning using self-supervision and things like that, right? And then this affinity relation can be latent, and then the affinity relation is learned from the data, right? And finally, the model is actually given by the neural network. The neural network is the model, right? Okay, and related to that, we need data sets, right? And there are different types of data sets. Besides images, then we can use, in this context, in machine learning, to do self-supervision, 3D model data sets, 3D scenes data sets, RGB image data sets, and video data sets. And this, we have like examples of these data sets in the course web page. And to capture and generate our data sets, we have different devices besides cameras, right? We have RGBD cameras like the Kinects and others, right? And you have LiDAR cameras that generate point clouds. And these are a device that are used for many applications in machine learning, like self-autonomous driving, things like that, to train these types of networks. All right. I guess we are done.